All right, continuing our investigation into quadratics, we're going to now look at dealing with quadratic inequalities. Now, quadratic inequalities can be solved a couple of different ways. One of them, the first one that we're going to look at, is graphically, which involves, of course, graphing the quadratic, which we know makes a parabola. And when it's an inequality on a graph, you have to do some type of shading to represent the solution set, all of the values that would work for that inequality. So let's look at that and talk about it first. To start off by doing this, we're going to graph the parabola. We'll find the vertex and the intercepts like we've talked about up to this point. And we're going to make our parabola. We'll make what we call a solid parabola, which is just a solid line like we would graph it anyways. If we have part of the function says y is less than or equal to, or y is greater than or equal to. If we have the or equal to option there, we're going to make a solid parabola. We'll use a dashed parabola if you don't have that or equals to. So for instance, you just have y is less than or y is greater than. And we'll look at a couple of examples like that, and I'll explain what the difference between a solid parabola and a dashed parabola are. Once we do that, we're going to shade the area on the graph that comes above the vertex of the parabola if the inequality has a y is greater than, meaning greater than or the option of greater than or equal to. And if it has a less than, y is less than the inequality or the quadratic, we're going to shade the area that comes below that vertex. And the word above and below, pretty much just a starting point here. I'll explain that a little bit more in detail here in just a moment, but basically we're going to make the parabola a boundary, and we'll start off shading above that vertex of the parabola if we have a greater than, and we'll shade all around the boundary from that point. And we'll start below the vertex with our shading if it says less than. All right, with that said, let's jump right in and look at some examples here, because it's probably a little bit easier to understand by looking and seeing the actual example worked out. Graph the inequality y is greater than or equal to x squared minus 7x plus 10. Well, we'll solve this just like we would otherwise we'll graph it just like we would otherwise by identifying the value of x at the vertex, and that would be using our negative b over 2a. Since b is negative 7 and a is 1, we have negative 7 over 2 times 1. That comes out to 7 halves, and we'll use 3.5 here for those of you that are fractionally impaired, and we'll use the decimal 3.5 to represent our x coordinate at the vertex. Continuing, we'll take that 3.5 now and plug it in to the function and find the y coordinate. That would be 3.5 squared, which I believe is 12.25, minus 7 times 3.5 plus 10. If I'm not mistaken, 7 times 3.5 is 24.5, so that's 12.25 minus 24.5 plus 10, and that comes out to be negative 2.25. So we do have an interesting set of coordinates for our vertex, interesting in that they're not whole numbers, and they're not exactly easy to graph, but we can still graph them all the same, following our rules by just simply saying that we're going to estimate where those coordinates would be. For example, 3.5 would be halfway between 3 and 4, and negative 2.25 would be somewhere between negative 2 and negative 3. So we'll plot our vertex there, and again, that's kind of an estimate as to where those coordinates would be. And we're not necessarily, if we had a need to be more specific, we would zoom in on it a little bit and get a more precise location. But for what we're doing right now, that's good enough. We also know that our y-intercept here is 10, and we'll plot that point. That's way up at the top of the graph here. And we also know that parabolas are symmetric, so we will make the mirror image of that around the vertex being in the center. We have an axis of symmetry, which is not plotted here, but it's going to tell us it's still there. We know that we have this point over here at 710, and we will use that to form our parabola. So what we'll do is we'll recognize that we have the greater than or equals to symbol. So going back to what we said earlier, that means that we will use a solid parabola. So we'll go ahead and make our parabola. I'll try and draw it. I missed the point there. Sometimes the smart board's not that easy to use. Okay, so that should go through this point. Just so you know, it's kind of messy, but we'll deal with it. So there's our parabola. And we now need to identify where we should shade. Anytime you graph an inequality, you're going to have shading somewhere. If you remember, we said that if we had a greater than or equals to, we were going to shade above the vertex. So we'll begin shading above our vertex, which basically just starts right above the vertex. And again, we're going to treat the parabola as a boundary, so we can't cross the boundary with our shading. And we're just going to go and fill in that whole area with our shading. And this is a very time-consuming task on the smart board. If you have a pencil or something like that, it's a little bit quicker. But you can see we have shading in here. And the shading represents all of the x and y coordinates that can go into this inequality and produce a statement that is true. So we can use any of the x coordinates or x and y coordinates that we shaded here to represent our answer. So again, we're basically just graphing the parabola like we did before, and we're adding in the shading. We're just going to shade above if it's greater than, and we'll shade below if it's less than. Let's look at one more example. We're going to now graph y is less than 3x squared minus 6x minus 2. To do this, we'll start off by finding the vertex. To find the vertex, we're going to do negative b over 2a. We'll use that technique again. Negative b would be negative 6, and a is 3 here, so that would be negative 6 over 2 times 3. And of course, that gives us 6 over 6, which is equal to 1. So we found that x is now equal to 1. To find our y coordinate, as you can imagine now, we're going to plug in 1, and we'll have 3 times 1 squared minus 6 times 1 minus 2. Well, 3 times 1 is 3 minus 6. That gives us negative 3. Minus another 2 would make negative 5. So we have the coordinates of our vertex being 1, negative 5. So we'll just plot that, 1, negative 5 on our graph, and we'll then use our y-intercept, which we can see from the equation as our c value, which is negative 2, and we'll plot that point. And again, if you remember, as we've talked about a lot up to this point, you have an imaginary axis coming through the middle of the parabola, and that tells us that we're going to have another point right over here. So we'll use these 3 points to form our parabola, and looking at our inequality symbol, we see that we have y is less than, not less than or equal to, but just less than. So that indicates that we should have a dotted parabola now, or a dashed parabola. So that's going to kind of look like this. And I'm not the world's greatest here at doing this, but I'm just going to make a dotted line. That's to show that our shading doesn't actually touch on this boundary. It's just kind of an imaginary boundary there. We come as close to it as we can without crossing over. So we're now going to look at where we should shade, and the shading, if it's less than, should shade below the vertex. Well, if you look below the vertex, we have this area down here, and again, we're going to treat that parabola as a boundary. So it actually does come up. It just tells us we should start going below, and we fill in everything else around the boundary. So that actually includes all of this area out here. And I'm not going to take the entire time here to color in this whole graph, but you can see all of this area out here would represent points for which the inequality would be satisfied. So we could use any point, x or y, x and y, plug them into this inequality and get a true statement. And that's what we're going for when we demonstrate the graph of a quadratic or a quadratic inequality, excuse me. All right, continuing along, we're going to look at the other method of solving inequalities, and that is algebraically. Well, we can solve an algebraic or a quadratic inequality through algebra by just manipulating some things. First off, we'll set up the inequality as an equation, and in doing so, that just means we're going to take the less than or the greater than symbol out and put an equal sign in there because we know how to solve that. And we'll get the equation in standard form and solve for x. Standard form again is ax squared plus bx plus c, like we've worked with so much up to this point. And we'll solve for x by using either factoring or quadratic formula. These values are what we call the critical values for x. So once we get our solutions for x, those are the places where it's equal to, we're gonna work with using those critical values to find the areas that it's not equal to. And we'll do that here in a second. I'll show you how that works. We'll test values in regions that are formed by the critical values. And we'll test areas out by plugging in values that fit into those regions. And we'll look at it here in just a moment. We're going to use a number line to do this. And then we'll identify all of the areas on that number line where the inequality is true. So let's look at an example here. It does get a little confusing, but the majority of this is stuff we can already do. So I am going to go a little quickly with the first part, which is something we've already learned. We're going to start off by jumping in and saying that's equals to, and then we're going to solve for x. Real quickly, we'll add 3 over to get 0 on one side. So we have x squared minus 10x plus 21. And hopefully you know the factors of 21 by this point that will add to give us negative 10. Tell us that this is going to factor into x minus 3 times x minus 7 equals 0. And our solutions would be then x is equal to 3 or x is equal to 7. Now, again, we've gone through this aspect of dealing with quadratics quite a bit lately, so hopefully you're familiar with it enough to get those critical values. And we're going to call those, that 3 and that 7, as I just said, the critical values. And we're going to go to a number line. And when we call these critical values, what we're actually saying is we're making these boundaries. These are areas where this would actually be equal to negative 3. And we want to identify the areas where that quadratic is less than negative 3. So what we formed is an area out here where the values are less than 3. We formed an area between 3 and 7 of the values that come between 3 and 7. And then we've got an area out here of values that are greater than 7. So we use those areas to define these 3 things right here. We have x is less than 3, which again comes into this area right here, all the numbers in that area, and of course that extends way out to the left over here as well. We have an area of values that comes between 3 and 7 in here, and we have an area of values that comes between, or excuse me, greater than 7, and those values are all in this section of the number line. So what we're going to do, and of course that extends out as well, what we're going to do is test values in each of those regions. All of those values in the region work the same way in that inequality. So we're going to test out 1 or 2 values and see which area works. So we'll start off by testing a number that comes in to the area of being less than or equal to 3? Well, for this, I picked 2. 2 is a value that is less than or equal to 3, so we'll try x is equal to 2. Well, we plug x is equal to 2 into that inequality that we started off with. So that would be 2 squared minus 10 times 2 plus 18. And we want to see if that comes out to be less than or equal to negative 3. Well, 2 squared is 4 minus 10 times 2. That would be 4 minus 20, which gives us negative 16, plus 18 is actually 2. So 2 is not less than or equal to negative 3. So this statement is false. Now what that tells us is that the section of values where x is less than or equal to 3 is not actually part of our solution set. Then we're going to test a value that comes between 3 and 7. Well, you can pick any value. That's 4, 5, 6. You could actually choose 5.28 if you wanted to, but we probably wouldn't want to do that. I'm going to choose 4 here. So we'll plug 4 into the equation, or the inequality. That would give us 4 squared minus 10 times 4 plus 18 is less than or equal to negative 3. 4 squared is 16, minus 10 times 4 is 40. So that's 16 minus 40. I believe that's negative 24. So we have negative 24 plus 18. That is negative 6. And negative 6 is less than or equal to negative 3. So this is a true statement. Our last section of values is x is greater than or equal to 7, so we just have to pick a value that is greater than or equal to 7 to test out. For this, I'm going to test out 8. So we plug in 8 into the inequality. We have 8 squared minus 10 times 8 plus 18. 8 squared is 64. Minus 10 times 8, that's 80. 64 minus 80 is negative 16. Plus 18 gives us 2. So we have 2 is less than or equal to negative 3, and that is false. So we've identified one section out of the 3 where our value was true, where when we plugged in x, the x that we had picked out, it came out to be a statement that was true. So well, we've identified this value, or this area. We're going to shade that area on the number line. So that area would be from 3 to 7 and everything in between. And we would just shade that on the number line to say that that represents all of the values of x that would work in this inequality. And hopefully you're seeing a little bit of that. Let's go through one more example here and help you to see it maybe a little bit better. Again, we've got an inequality. X squared minus 6x plus 10 is greater than 2. You can, first off, we want to jump in and make that an equation so that we can solve it for our critical values. We'll subtract 2 over, so we have x squared minus 6x plus 8. We're now looking for factors of 8 that will add to make negative 6. So we'll use x minus 4 and x minus 2. That tells us real quickly that x is equal to 2 or 4. Those are your critical values for this problem. So now that we've identified those, we're going to go to our graph of our number line and imagine our sections being created. We have a section out here of values that are less than 2. We have a section of values that come between 2 and 4, and we have a section of values that are greater than 4. And we're going to test a value out in each of those. So, looking real quickly, again, x is less than 2 is out here, and a value between 2 and 4 is this little area in here between those two values, and then we have a value out here that is greater than 4. And we want to test a number in each of those areas. So our area first to test will be less than 2. So I chose 1, or excuse me, I chose 0. That's a quick one to try if you can. We plug 0 in, that's going to be 0 squared minus 6 times 0 plus 10 is greater than 2. Well, that's 0 minus 0 plus 10. That gives us 10 is greater than 2. Well, is 10 greater than 2? Yes. So that is true. So we have a true statement here. So we'll set aside the fact that we know that that one works, and we'll come back to it in a minute here. Now we're going to choose a value that comes between 2 and 4. And not a lot of selection there. We'll just pick the one obvious value, which is 3. We plug that in. 3 squared minus 6 times 3 plus 10 is greater than 2. That's 9 minus 18, which is negative 9, plus 10 gives us 1. And 1 is not greater than 2, so this is false. So we rule out that section of the graph. And then we're going to try the other section, which is x is greater than 4. So we'll choose 5. That's a value that's greater than 4. And we plug that in. 5 squared minus 6 times 5 plus 10 gives us 25 minus 30 is negative 5. Plus 10 would be positive 5. So 5 is greater than 2. That is true. So we've identified, actually, in this case, 2 sections that are true. So what we'll do is we'll plot those on our number line. Notice in this case that I'm using open circles because we did not have a greater than or equal to. We just had the greater than. So when we have greater than, we use open circles. And we have to signify that we're not actually equal to those numbers. So we went less than 2, so that region was true, so we'll shade a line out there, and then we'll shade a line out greater than 4, where that region was true, and that is what our solution set looks like. So that gives us our number line answer, or our answer in the form of a number line, and we have answered this algebraically. Well, I hope you got a little bit of this, and we'll take some time and continue to look at this in class, and I hope you can make it through and find some success here. Please ask questions in class, and I'll talk to you soon.